Today we will begin with the analysis of another converter, which is edge bridge converter. Edge bridge converter is a very popular converter and it is used in many different applications. So, this is the another converter which we will be using as an example to explain the concepts of design. So, before doing that we will be analyzing this converter. So, this is the circuit of edge bridge converter. What you see here is that it has got 4 IGBTs. Now, 4 MOSFETs may also be there, it depends on the application. Here I have shown 4 IGBTs and then there are 4 anti-parallel diodes. So, this one TA plus and TA minus, that is how it has been named, the upper one and the lower one, and these two connected together, this is called as the leg A. And similarly TB plus and TB minus, they connected together, they are called as leg B. And the midpoint of this is named by the symbol A, and midpoint here, this is named by the symbol B. Then this is the DC bus and denoted by P and N, and then the load is connected between these two nodes A and B. So, this voltage, this is the voltage between VAB, which is denoted by VO, and the load current is your IO current. And these diodes are named similarly as the transistors, like DA plus, DA minus, DB plus and DB minus. And the current through this DC bus is denoted as IDC. So, now let us begin with the analysis, and before that just also you may be knowing that this is also called as full bridge or it is also called a single phase inverter. And there is one rule which has to be followed, that is both switches of one leg cannot be on together. You can see here that if you turn on both of these two switches together, what will happen is that it will lead to a short. So, that is why we always ensure that these two switches cannot be turned on together. So, excluding it, what are the different possible switching combinations that we can see? Let us write down. So, possible switching combinations. So, first what we can see is that this TA plus and TB minus, these diagonal switches can be on together, and the other two diagonal switches, they also can be on together. Okay. So, TA plus TB minus is one switching combination and TA minus TB plus, this is another possible switching combination. So, TA plus and TB minus and TA minus and TB plus, these are the two possible diagonal switching combination. Next, what we can see here is that these upper two switches can also be on together, or these lower two switches can also be on together. So, third possible combination is TA plus and TB plus, that means both upper on together, or TA minus and TB minus, it is both lower, that also can be on together. So, these are the 4 possible switching combinations for edge bridge converter. Now, let us look into each switching combination and the corresponding equivalent circuit. So, let us take the first one, which is your TA plus and TB minus, these being on together. So, here when this is shorted, TA plus and TB minus, this can be shorted. Okay. Now, the diode may also be conducting. We will see that when the diode conducts and when the transistor conducts, but to draw the equivalent circuit, we can consider these as shorted, right, because we are considering it to be ideal. So, then let us draw the equivalent circuit. So, the equivalent circuit will be like this. This is VDC and here this is the output voltage VO, and these are the ones which are turned on. Now, let us see what happens when, what is the direction of the current. Let us say this direction of current is positive. So, if this is the direction of current is positive, what we will see is that the current will flow like this. It will be supported by the transistor and then it flows through this path and it comes back here, and then again it is the transistor only which is going to support the path of the current, right. So, what we observe from here is that when the switch is on, it is the transistors which are carrying the current and not the diodes. So, TA plus and TB minus are conducting when your current is positive. And what is the voltage across output here? What we see, these two are shorted, right. So, the output voltage VO is equal to VDC, and what will be the current? This current over here, IDC current, is the same as the load current. Okay, this IDC current is the same as the load current. So, therefore, what we can write it is that IDC equal to IO. Now, let us see what happens when the current direction is opposite. So, when the current direction is opposite, the current flows like this, it has to come here, and then since it is flowing in the opposite direction, it will be flowing through this diode, it will come here and then it has to go again through the diode only because it is in upward direction and it flows through the load. So, this is the direction of the current. So, that means what we observe here is that now the current is carried by the diodes. This current flows like this in the opposite direction when the current is negative. So, the current is carried by the diodes dA plus and dB minus when current is negative, and these two, your VO equal to VDC and IDC equal to IO, these two remain same irrespective of the direction of the load current. Also, one more thing that we should see is that what is the voltage that is blocked by these devices. So, what we see here is that from the very equivalent circuit, what we can observe is that the voltage these non-conducting devices have to withstand is equal to VDC, because this is shorted to VDC, and so here what it has to block, this has to block is equal to VDC, and this is also shorted here. So, this has to block the voltage VDC. So, the non-conducting devices have to block VDC voltage, and the conducting devices have to carry the current IO. So, non-conducting devices they block VDC voltage, and conducting devices they carry IO current. That is what we have to remember, because this is what we will be requiring it when we draw the waveforms. Next, see another the second equivalent circuit for the second switching combination, which is the other two diagonal devices TA minus and TB plus. Now, what happens is that let us say this is the direction of the current. So, what will be happening is that this is on, this transistor is on. So, if this transistor is on, the current is positive, it flows like this, and it has to then be conducted by the diode. It comes like this, and then this device is on. So, this also has to be carried by this diode. Okay, so, this is the direction of current when two transistors TB plus and TA minus are turned on for current to be positive. So, let us draw the equivalent circuit. So, the equivalent circuit can be drawn just by shorting whatever has been turned on. So, here one is turned on, here one is turned on, and this is a VO, and using this what we observe is that VO, this is coming here, this point is connected downwards, connected to the negative terminal, and this point is connected to the positive terminal. So, the voltage VO will be equal to minus of VDC, and IDC current, what we can observe is that opposite to the load current. For example, let us say if the current is positive, we just saw now current is positive, how it is flowing is like this, these diodes are carrying the current, right, and so it is this IDC is opposite to IO. So, therefore, IDC equal to minus of IO, and when the current direction is positive, the devices that are conducting is DA minus and DB plus when IO is positive, and when IO is negative, IO flows in the opposite direction, it flows like this, it has to be then carried by the transistors. It flows like this, comes here, goes down, and here also the path of the current is downwards. When the path of the current is downwards, that means it has to be carried by the transistors. So, then your transistors TA minus and TB plus are carrying the current when IO is negative. And the blocking voltages for non-conducting devices remains same here, it is equal to VDC, and the current that is carried by conducting devices is equal to IO. Now, let us look into the third switching combination, which is both the upper switches being on, TA plus and TB plus. Now, in this case what will happen is that both of these upper two are turned on, so it will be like this, right. So, accordingly we draw the equivalent circuit. So, these two are turned on, this is here VO, and what we observe here is that both the terminals of VO are connected to the same bus. So, therefore, VO equal to 0, and IDC also we can see that here IDC equal to 0, and when the current direction is positive, what we can observe is that it is flowing downward, that means carried by the transistor, and here it is carried by the diode. So, TA plus and dB plus are conducting when IO is positive, and when IO is negative, that means it is flowing in the opposite direction. It flows like this, it will be coming over here. So, then what we observe is that it is TB plus and the diode DA plus which are going to conduct. So, DA plus and TB plus are conducting when IO is negative, direction of current is negative, and the blocking voltages that remain same for non-conducting devices, and which is equal to VDC in this case also. Now, the fourth combination, which is your TA minus and TB minus, the lower two switches being on. At that time, what we observe here is that the path will be like this, right. This is the circuit, the path that is going to be followed. So, let us draw the equivalent circuit again. So, the equivalent circuit will look like this. So, this is here VO, and VO again will be equal to 0, we can see that clearly, and IDC also will be again equal to 0. When the current is positive, what happens? It flows like this, right, it flows downwards here, and here it flows upwards. That means it is the diode DA minus and the transistor TB minus which are going to conduct when the current is positive, and when the current is negative, it is flowing in this opposite direction, it flows downwards here and flows upwards here, and then it is conducting in this way. So, what we observe, it is the other two devices which are going to conduct now, TA minus and dB minus, which is carrying the current when IO is negative. So, we saw all the four equivalent circuits. Now, you should be already familiar with the term pulse width modulation. In short, it is also called as PWM. So, what is PWM is basically you have a carrier signal, this kind of a carrier signal which may be of triangular in nature, or sometimes sawtooth is also used, sawtooth wave shape, and this has that frequency which is your Fs equal to the switching frequency, and it is compared with a reference. Now, let us say this is your reference, you can call it as a VO ref, and we can call this as V carrier, and then these are compared. So, here this is how you compare it. And we may use a logic that whenever this VO ref this VO ref is greater than V carrier, at that time it will be high, the gate pulse, the pulse will be high. So, accordingly what we can draw it, what we can draw is like this, it will be 1 when VO ref is greater than V carrier, else it will be 0. So, we will be getting a pulse like this, and this is also called as the gate pulse because this is given to the gate of the IGBT or the MOSFET. Okay, so, this is the gate pulse. So, this is what is your pulse width modulation PWM, and there are different types of PWM methods. For edge bridge converter also there are different types of PWM methods that are used. There are different ways in which modulations are performed, not necessarily always pulse width modulation is going to be performed, other types of modulations are also there. So, we will not be looking into all of them, but we will be looking into the ones which are very much used and are very popular. So, there are two main types of PWM for edge bridge. One is called as bipolar PWM, and it uses these two combinations, the diagonal ones TA plus and TB minus and TA minus and TB plus. These two switching combinations only it uses, is called as bipolar PWM. And there is another one which is called as unipolar PWM, and it uses all 4 switching combinations. And depending on the modulation method that we use, that affects the waveforms of the voltage waveforms, the current waveforms across different components, and then it affects the design process, because once your waveform gets modified, what is the voltage, current, the frequencies the device has to withstand, the component has to withstand, that changes. Then accordingly your design also changes. So, that is why we will be also paying attention to the modulation method. So, what are the key points of this lecture is that when you take any converter which have got multiple switches, then you see what are all the different possible switching combinations for that converter, and then for each of the possible switching combination you analyze the equivalent circuits, and then you find out the different voltage and currents that are flowing through different devices and components, and that will help you in finding out the ratings of the devices during the design process. Thank you.